A force F is created when two charges of charge C are separated by a distance r. By what factor would the force change if one charge was doubled and the distance was doubled? Okay, so I'm going to go over two ways, and you guys can pick your own personal preference when you try to find these proportional relationships. But here's what we know. We know that F equals K times the two charges, I'm going to call them charge 1 and charge 2, over their distance squared. Okay? So we have charges, charge C, separated by a distance r. So I plug that in. So if I'm doubling only one of the charges and I'm doubling the distance, what two variables are constant here? K in one of the charge values. So that means I'm only going to have C2 and r squared that are going to actually impact my new force. So my new force is going to be proportional to C squared over r squared. So my new force, F prime, what am I doing to that other charge? I'm doubling it. So this is 2C2. What am I doing to the distance? Also doubling the distance, but remember the distance is squared, so that's 2r. So then I get 2c2 over 4r squared, which is 1/2, but c over r squared is my original force representative. So my answer is it's going to be half as much force if I double a charge and double the distance. Okay, so that's one way to do it, though some of you guys prefer to set up a ratio of the two. So if we were looking at that instead, you'd start the same way. So F equals K, C1, C2 over R squared. F prime equals K, C1, 2 times C2 over 2r quantity squared. So then what would happen is the k's would cancel, the c's would all cancel. So what it looks like is then I get F over F prime equals, on top here I have 1 over r squared, over on top here I have 2 over 4r squared. But what I can do then is take my 1 over r squared and multiply by the reciprocal. So that's times 4r squared over 2. So then what I'm left with is F over F prime equals, well, the r squareds will cancel, and 4 over 2 is just 2. So to solve for this here, I just multiply by F1, so I get F equals 2F prime. I'm trying to solve for F prime, so F prime equals, if I divide both sides by 2, it's going to equal 1/2 F. Okay, so two ways, same problem. And then the last example for today, we have two charges, 1 and 2. They're on a straight line 6 meters apart. So let's go ahead and draw this. So we have Q1 and Q2. And Q1 is -9 coulombs, and Q2 is -5 coulombs. And then it says, where could we place a third charge, -2c, on the line here, such that the net force is equal to 0? Well, if the net force is equal to 0, what do I know about the forces? They have to be equal to each other. Because when we add them together, they need to be equal and opposite. So the two charges will be equal in opposite direction. Now, in terms of the AP, I don't think they're going to have you actually do the algebraic work here, But conceptually, I want to talk about really quick all the relationships of where this charge could possibly go. So just taking a side look at this, I have a negative charge and a negative charge, right? And I'm adding a negative charge to this line that they're placed on. Make sense? So if I put the negative charge over here, okay? So this is also negative. What is this charge going to do to this? Push or pull? It's going to push it away. Make sense? What is this charge going to do to this? It's also going to push it away. So these are in the same direction. So for this particular example, if I put my third charge to the right of these, I'm not going to be able to get a net force of 0 because both forces are in the same direction. Likewise, if I come over here and I put the force over here instead, or the charge over here instead, again, negative charge, this will push it to the left. This one will also push it to the left, so there's no way I can get a net force of 0. I have to put the charge on the line. So here, I'm trying to find this charge. I'm going to place this over here. I'm trying to find Q3, which is equal to -2 coulombs, right? And what happens here now is this charge, Q1, pushes it to the right. This charge pushes it to the left. I now have opposite directions for my forces. So it has to be in between the two charges. Okay, so that's a big picture idea. We're going to go ahead and solve this algebraically, but I highly doubt that it's going to ever have you do that. So it may say, hey, like, where would the charge need to be located so the net force is 0? It would have to be in between the two. Why would it have to be closer to the second charge? Why closer to Q2 versus Q1? Excellent. We have -9 coulombs as a charge here, which is a greater charge in comparison to -5 coulombs. Okay, so if I'm trying to set these equal to each other, if they're equal and opposite forces, I need to make sure this is closer so that I'm increasing the distance here. Okay. All right. So the distance between them. What is the distance between the two end charges? 6. What is the distance here then? We actually don't know, and that's funny because that's what we want to find. We want to figure out where that third charge can be placed so that the net charge is equal to 0. If we don't know a distance, what is a good representative for that? D for distance, you bet. All right, so we're going to make this D, which makes this what is this distance then? 6 minus D. Good? Okay. All right, so we want the charges to be equal, so we know the net force is 0, so we know that F of 1 on 3 has to equal F of 2 on 3. All right, so using that, let's find F of 1 on 3. F of 1 on 3 is going to be K, and then I'm going to put times 9 times 2 over D squared. Now, why did I not put -9 coulombs and -2 coulombs? Because it's the magnitude. When you use the force for electrostatic equation, it's always a magnitude. You can put negative, but then you need to include the absolute value, and when you take the absolute value, then we'll come back to this +9, +2, okay? And this is going to be equal to K, and then now we're looking at the force from charge 2 onto charge 3, so that's times 5 times 2 over the distance, but what is the distance between Q3 and Q2? So this is 6 minus D quantity squared. Okay, so here the k's cancel out very conveniently. So then we're left with 18 over d squared equals 10 over 6 minus d quantity squared. What would be the next step? I'm going to do one thing before I do that. We could either distribute this part, or what would be easier? Take the square root of both sides. So I'm going to start by doing that. So then we're left with root 18 over d equals root 10 over 6 minus d, and then now's a great time to go ahead and cross multiply. So when we cross multiply, we get 6 root 18 minus d root 18 equals d root 10. What do we need to do next? Excellent. We're going to add the d root 18 to both sides to get our variable on one side of the equation. So we have d root 10 plus d root 18. Now what? Factor out the d, and we get root 10 plus root 18 over 6 root 18. Last step. You bet. And then we're going to plug that all into our calculator. And then when we do that, what happens is we are going to get d is approximately 3.4 meters. Now that's not the answer. It says, where could a third charge be placed on the line such that the net force is equal to 0? If I say 3.4 meters, that's not enough information to answer the question. Now, depending on how you drew your diagram and set up your x versus 6 minus x, you're either going to get 3.4 or 2.6 for your answer. So you need to be a little bit more specific. So Q3 will be in between Q1 and Q2 and placed 3.4 meters away from which charge, you guys? From Q1. So if we had flip-flopped this, if we made this 6 minus d and this d, we start the same, but then we would say, and would be 2.6 meters away from Q2, and that would also be a correct answer. Okay, so just make sure you write enough to describe it accurately.